was corresponding. If it was for three, like the contribution with three particles in the intermediate flux state now. I will try to avoid a bit here. So, okay. Now I will write. So now I will have like the sum over three particle flux states. So now this guy will contain a symmetry factor and then a symmetry factorial, and there will be integration over with three such integration for each of the intermediate particles. So I will just write a compact notation. So DUA that will mean this whole thing here. Like the integration. So now I have three particles, so that means that we have integration DUA.
Sorry, is it possible to light up the light on the backboard? If I do, then the people there will see this. I was like, okay, what is it? It's not compromised. We can try.
So here I've written these three particular state here, and now again. And now now I have the one of the so this TABC is just a form of such P squared and the square plus for each of the three guys. So now the problem is that here we have two particles on one side, three on the other side, whereas the vertices are only 2 to 1 and 1 to 2. So basically, each time there is there should be one spectator particle. So basically, either the three, or either the one or two should not participate to the first scattering and should just go through. So it should be contracted directly to one of these guys as a commutator. So that would just be the same, and then we would get three, vertex, and then on the other side, same story. So, so basically, by doing this, okay, we can have either the one or two, which can be spectator in the third vertex, and then either 3 or 4, which can be spectator in the second vertex. But okay, like. The two traits are independent, so actually out of this we can have like four contributions. So so here if I And now, what happens is that here, so if I consider first the contribution with so with 2 which become C here equals C. So that would be just spectators that will be removed from this vertex. And okay, if it's so I choose 2 as a spectator, but then I have 3 places to contract it. So either A, B, or C. I choose C, but then because that's completely symmetric, but then that would give me a factor 3, like this 3 contribution after this choice. And then, okay, that means that now 2 will appear here as that would be A2 dagger. And then we would need again, for example, 4 to be a spectator, so that will give me, so this would have to be contracted with one of these guys to be spectator, but in order to get something connected, it cannot be the same as the one I had before. So it would be A or B, there are 2 choices, I choose 1. So that would be, so now that would be or B here. So by doing this, I get each time a commutator which removes such integration here. So in the end, I have only one integration left. And so here, so the first contribution here is with this. We will get that. So here the 4 was removed, so there is only 3. And now on the other side, so A is there. Was a piece, so the 4 B is removed, and the C was now here, 2, so the C is removed because it was spectator, and then we have the P, which is and now we still have the 1, or the P was spectator in this case. And now, okay. And now A and C. Now, okay, there is a contribution from A. The contribution from B and C, so that's actually 2 and 4. So or minus. And it's 1. So that was one of the contributions. And okay, sorry. And then since I was telling that there was each time 3 possibility to choose with which one to contract, and then there was 2 left because we already removed 1. So then basically that would be a 3 factorial here in the front, which would cancel this guy. So here there are other contribution here. So that would be this, and then we would have similar contribution with okay, so this was we've taken 2 and 4, 2 spectator here and 4 here, so then that would be okay, also possible choices. What's going on now? Okay, so now here we can just plug the vertices we have. Okay, so I mean, anyway, so the same thing will happen. That's so we would get okay, obviously a G from each vertex, and by combining the two-time delta function. Here we would get one. We can rewrite one as one delta 3 as overall one conservation in order to put it with this guy in such a way.
I'm sorry, is it plus three other possibilities or two other possibilities?
So yeah, so this one is so three other terms. So we have here either either 1 and 3 as spectators, or we have 1 and 4, or we have yeah. So yes, so here it was 2 and 4, which were spectators, so 2 here and 4 here, or we have this other check. And each time they come with a 3 factorial, which combine this. Okay. Okay. So here, in each term, we will get eventually into the 4, like the, sorry, 4-dimensional one conservation here. Well, so the 3 factorial will be removed. And there will be also a 2 pi to the 3, which will make this integral possible. But okay, this integral is something like this, but okay, if you have only that, you see that you get rid of that part, but there is still the theta over 2t plus, which is still there. So now I will write directly what you get from this guy. So you get theta over 2p plus, theta of pa over 2pa plus, but in that case, the a, so that would be p1 plus p4 plus. So because of this, here you have a conservation that will give you that p1, that in terms of plus and complementon, that p1 is going to a and 4. So a is 1 minus 4. Yeah. So that is what is left from the integration measure. And then the only thing which is remaining is energy denominator here. But here you see that okay, the P2 minus is cancelling here. So what is left here is P1 minus, minus P4 minus. And then the A I was telling it was A was 1 minus 4. So it's 1. And okay, so and okay, again without so here again you see that we have these 2 p1 plus minus p4 plus that we can take inside, so that we remove this the denominator, and then from this times this and then minus the square, we will reconstruct the fundamental square here. And since this guy is supposed to be positive, we can also multiply by epsilon and we still keep epsilon. That will be the result for that contribution. And okay, I can also write the terms for the three other now explicitly. And the calculation way is the same way, but I can just leave this in the result. Yeah. So we get these four terms here from the contribution where we have three particles in the intermediate flow state phase. And now, okay, we can use like the overall formula conservation here to rewrite the guide. And so typically from this, we have the relation that, for example, 2 minus P4, 2 minus P4, that's 2 minus P1, and minus P3. Okay. So now if we rewrite this, so that's two particle contribution here. So now we have P1 minus P4 here. Oh, okay, I'm going to do that a bit. But you see that this term now and P3 here. And then when you take the square, that's the same denominator, so you can put them together. And now if you put the numerator, we have P1 minus P4 here, P1 plus minus P4 plus. No, sorry. Yeah, so that one was. Yes, so that one should be 3 and this.
Yes.
So this P2 minus P3, that will be P4 plus minus P1 plus. So that basically is theta of the opposite of that. So we have theta of something plus theta of the opposite of that, that's just 1. So here. So here, so this guy and this guy will group into that term here. No? And now seems to me with these two, okay, that would group. Okay, we can group them in the same way as 1 minus P3. So that will be the final result. And here, if you think about it, you see that in terms of Riemann diagrams, it's with operators as well. And now that would be something like key channel is changed here. There's 1, 2, 3, 4. So that's here. So propagating line here that went on 1 minus 3. So that's the channel, and that's guy here. That will be the same, but with 1, 4 here, and 2, 3. So this I guess would be what channel. And that's indeed the 3 contribution that you expect in the series from 10 language. But here you see, funny point is that in this case, since in light front, like vertices are ordered along this plus, like this T channel and E channel contribution here, they are actually this one, so the T channel, it's just expressed as 2 different contributions here. One like this, 1, 3, 4. Whereas this vertex is before than this one in terms of plus. And another contribution where we have the opposite. So 1, 3, 4. And here the intermediate state is between the 2 vertices. So here the intermediate state is you have particle 3. Now you have particle A here. So 3 and the 2. So 2 and 8. Whereas here, the intermediate state here, you would have so you have 1, 4, and 8. And now, okay, so here the momentum would go down here. The momentum flow will be downwards here, whereas here it will be upwards. So basically, in light function 3, because we have the ordering in terms of x plus, it means that we have to distinguish like the momentum flow of the line. So basically, the sign of the k plus in the intermediate line, and that's precisely this thing here. We were seeing that we had separate contributions depending on the sign of the momentum flow. So that's how you get. You get it for one Feynman diagram, you get several light front diagrams because you have to distinguish this ordering and for at least a sign of the plus momentum flow. And just this guy at only one term because like the only possible other way to order would be if we have something like this. So this guy is merging, and if we put this vertex after this one, basically. But that is not allowed because then you would have here 3, like the sum of 3 P pluses, which would be all positive and which would be equal to 0. And here, same story here between the 3. So this is not allowed in that form. So we have only one diagram from the channel. So okay, so that's typically how things work. Of course, when you play with the rules. Of course, this example is a bit trivial because it's actually much easier to do standard Feynman rules in that case. But okay, I think it was illustrative enough. And yeah, and once you understand this story, actually you don't need to write the full internet for state with all the spectators, because eventually you know that by combinatorics they will just drop. So instead of writing this, you can immediately write the four separate contributions. I mean, you can just write down the diagram, so this, and then the other two diagram for the loop channel. And then instead of writing this complicated vertices with too many particles, we can just write 1 to 2, and here 2 to 1 vertices only. And then summation over the Fock state, which will be not the 3 particles, but just the one which is not forced so far. So just so that will be a one particle Fock state with some other, like just the internal line. And then the only thing, so basically it's as if you had only one particle Fock state instead of 3. But the only difference is that in the imaginator, you have to remember what you have to look in your diagram, what is the intermediate state and what it contains, and then put the contribution not only of the particle integrator, but also of the other guy to play the role spectator, and then you get this. So that's how we can play with light front boost to calculate scattering amplitude, or then the case of light front wave function is very similar. Okay. So that was the part of the application. So now we will switch to the back to the notes and go to the Fermion case.
That's me.
What? Yes.
Just take it.
Okay, so far we talked only about scalar theory, but okay, like this week it's supposed to be about QCD as well, so let's slowly move in that direction. And slowly, because here we'll first talk about 3 direct Fermion fields. So yeah. Fine or
No.
okay. Yeah, so okay.
Yes.
I know it's off.
It's off. Yes, should be.
Okay, now
It takes a moment. Just
yeah, okay. So anyway, yeah, okay. So here we have the usual Lagrangian for free direct field here, and with this equation of motion, so this is well-known like direct equation basically for free field. So in light front quantization, actually, in order to discuss like the dynamics of this in the front form, so with evolution along the X direction, it's actually okay. Just when you think that it's quite important to produce two things here. So these 2 objects. So I mean, you know the usual gamma matrices. So here that will be just gamma minus times gamma plus over 2, or gamma plus gamma minus over 2. And of course, we have the standard anti-commutator for direct matrices. So if you just play with this, you can convince yourself that these 2 guys actually here are projection in the sense that if you multiply twice by this, it's the same as multiplying once, or same for the other guy. and that in addition, there are also complementary projection in the sense that, okay, if you apply both of them, then you get nothing. And if you sum over the two, you get identity. So it's really, so this is really projection which splits your Dirac field or yeah, I mean a spinor field or into two pieces. Okay, so you can apply to the field and you get so-called psi G or psi B component. And okay, so here you have the rules of how to deal with it. So how it affects also the conjugate of the bar field. Okay, fine. But okay, why do we do this? Is okay when you have this equation, a Dirac equation. Just okay, if you one important thing to remember is that just by looking at this, if you look at this standard relation for mu and nu equal plus, what you would get in that side would be 2 gamma plus, and here you will get 2 G plus plus, but then G plus plus is 0 so because of Light-Cone coordinates, and so that means that that gamma plus times gamma plus is 0, and then the same gamma minus times gamma minus is 0. So that's a very important thing to keep in mind when we play with Dirac field in Light-Cone coordinates. So in particular, if you take the Dirac equation and you multiply it by gamma plus, okay, you can write separately all the gamma mu, d mu, all the coordinates separate, and you see that there was a contribution which used to be gamma plus and the relative respect to x plus, but then it's killed by the multiplication by the gamma plus here. So okay, so we have only these three terms. And now, if you play with the projection here, you can see that actually, so this corresponds to having this term here with so this gamma plus gamma minus, that would be just effectively that would be so that gamma plus gamma minus, that would be just twice this PB projection. So we get only the field here with the minus derivative. And here, okay, we get something which eventually, since there is a gamma plus, that will select the G component here. So okay, so that's one projection of the Dirac equation here. And the important thing that Dirac equation is supposed to be an equation of motion, but here in this projection there is no derivative in x plus. So this is actually not an equation of motion anymore. It's a constraint equation in the front form. So when you think of evolution along x plus. So on the other hand, if you multiply by gamma minus instead of gamma plus, okay, there is something, okay, you get similar simplification, except that now you remove the term with the minus derivative, so you get only the plus. And now, okay, eventually you arrive at this. So now you see there is a derivative in x plus for psi G components, and that for the psi B. So now that's basically, instead of having one Dirac equation for field in which have 4 components, now we have 2 coupled equations for like field projection, which each have two components actually. Okay. And there is only this guy here as a derivative respect to x plus. So in that sense, it means that only psi G is a standard dynamical field, whereas the psi B here is an auxiliary field here. There is it has no plus derivative acting on it. So because of that, okay, then we use this notation where we say G is for good, so we say it's a good component of the field, and B is bad, so it's just auxiliary, so there is no real dynamical content in there, so it's okay. And it means that, okay, it's only psi G which will be in principle, important object, and psi B, okay, we still need it because it appears here. But okay, we can use this constraint equation to determine these bad components in terms of the good components, but for each on each hypersurface of constant x plus basically. And the only thing is that it requires to invert this, I mean, to integrate along the minus direction. So basically invert this derivative. So here we write it formally as this, but I mean, it's using the same notation that I was introducing yesterday. So if you want to be precise, so this would be a kind of non-local, I mean, so that would be kind of a convolution along the minus direction here. Okay, so that would be kind of something non-local here, yes. But okay, that's still okay. That would be the how we can get the psi b in terms of psi g on a given x plus alpha surface. So okay. So then we have only this good component which are dynamical. So we can still look at the like the momentum density conjugate here with respect to that. So if we take the derivative of the Lagrangian with respect to the plus derivative of this psi g, we get this. Okay. And then okay, so this, because it has the bar here, and I mean it can be considered independent of compared to psi g, and then we can really apply very standard anti-commutation rules. Now we have the field which has zero anti-commutation with itself, this psi plus which has zero anti-commutation relation with itself, and then the field and its psi plus here have a non-trivial commutation relation, which is just basically I times delta function along the, like, so yeah, so all these are equal time commutation relation, but time meaning here Light-Cone time, so basically x plus equal y plus in all of this. And then you have delta along the other directions, along the minus and perp direction. And you have like identity matrix in the space of this good component. So it's actually the projection operator here. So this is just a 2x2 identity matrix, if you want, which would be a block inside the okay, yeah, it's so Dirac field has our four components. So gamma matrices are 4x4 matrices. So here it's a 2x2 identity embedded into this 4x4 type of matrix. Yes. Okay. So just okay. Here it was a bit annoying with I and the gamma plus and so on. So by just playing with the gamma matrices and algebra, we can rewrite this okay, like equivalent equation to this anti-commutation with either just the psi dagger or the psi bar if you need it. So it's there as well. It's completely equivalent.
We could have defined the good ones as the bad ones, right? So since we have a connection,
I mean,
define the bad.
So the thing is that it depends what direction you want to, like, along what direction you want to describe your evolution.
If you have to
So
the x plus, we have to use the gamma plus multipliers. So
if you think of evolution along the x plus direction, then okay, like the Dirac equation contain derivative with respect to x plus only for the psi g. So it's this one which is a dynamical field, so not the B. If we were doing other, I mean, we can also do another formulation of light front where we take instead minus as an evolution variable, and then that would be reversed. And yes, that's true. And but okay, here in terms of plus, if we choose to describe evolution along the plus direction, then we are forced to have a psi good as a dynamical component, but yeah, that indeed that's kind of an arbitrary choice, but which is fixed once you choose to the x plus as time. Yes. Okay. So now that we have this, okay, we can write down the current, like, okay, current associated with the Poincare transformations. So we have the T nu, so it can be obtained with the usual formula, and okay, so here we have this expression. Okay, fine. For the current associated with the Lorentz transformation, now in addition to this orbital type term, we have also the extra term associated with okay, with the transformation of the spinor here, and that's with the thing I was telling you yesterday morning here. Okay, we have this. So this is basically the 1/4 of this of this commutator. Sorry. Okay, so once we have this, we can just write down the, for example, the P plus or P perp component of the charge here. So so again, it would require to have a plus component here. So for gamma, so we have mu equal plus, and then we have either mu equal plus or j. So in both cases, again, like this term will drop. So no Lagrangian term here. So that would still be valid. Okay, so we have only this term which contributes. And so then that will be d nu, which would be a derivative either, I mean, yeah, so we have this term basically for both cases, for nu equal plus or j. So eventually that would be either a transverse derivative if you look at pj, or if you look at p with upper plus, that would be derivative with derivative respect to x minus eventually. So okay, I have only this, and you see here the thing is that since there was because like the charge are defined here with a plus with the first component of the T mu, which would be plus, it means that there was a gamma plus here, and this gamma plus is actually projecting out the bad component and keeping only the good component here. So only the good component appear in the P plus and P and transverse momentum like Poincaré charges. And similarly, if we look at this guy here, which is for which correspond to this transverse Galilean boosts. Now we have again the first one, which is plus, and then we have plus I. So here the first is so for example, if you look at this term here, so the rho will be plus, and then another one will be plus, and another one will be I. But then gamma plus anti-commute with gamma I, and gamma plus equals 0. So basically, this whole term, this extra term, will entirely drop for this particular transverse Galilean boost, and we will have only the orbital-like term surviving, and okay. So then that would be similar to this guy here, but with just this x in addition. So okay. And again, there is a gamma plus matrix here, and no other gamma matrix. So basically, the bad components are projected out, and in this kinematic charge for kinematic transformation here, like this Galilean boost, we have only the good component appearing. Similar story for the IJ, so for the rotation within the transverse plane, except that now here we would have gamma plus, gamma I, gamma J. So now this guy would survive. There is only one gamma plus, and so that's this extra term here. We have gamma plus and then gamma I, gamma J. So now you have this. Yes, okay. And here, okay, fine. So overall, there is only one gamma plus and no gamma minus, and all the other are gamma perp. And because of that, again, the bad components are projected out. We get only the good components. So you see that all this for all this Poincaré charge is associated with kinematical transformation, which preserve plus equal constant Altair surface. They can be expressed in terms of the good component of the spinor field only. So okay, again, that's a dynamical like part of the field. So okay, so this is fine. So you see, I mean, okay, like this, yeah, sideband is auxiliary field, and it doesn't even appear in all this kinematical transformation here. But now, if you look at, yeah, yeah, so now, if you can write down the corresponding quantum version of this, But okay, it's a bit annoying to write because it would require to anti-symmetrize the psi and the psi g and the psi bar g as quantum operators. But still, okay, you need to keep that that matrix multiplication, like in terms of direct matrix multiplication. Okay, you need to keep that ordering. But in terms of as quantum operators, they should be anti-symmetric. So you need to add extra indices and so on. So yeah, but in principle, you can write that. And then by playing with this anti-commutation relation here, you can in principle check that you get all the proper commutation relation between these kinematic generators and the field, in order to generate like kinetic Poincare transformation in a correct way, and also the kinetic part of the Poincare algebra and so on. So this, okay, it's a lot of algebra, but okay, that can be done, and there is no problem in that. So now, if we look at dynamic chart, for example, the P minus, okay, so this contains a plus minus component of T mu nu, which plays all of light front Hamiltonian density. So now, if we write this guy here just from here, so that would be plus here and upper minus here, which means the lower plus. So that would be the with respect to x plus. So now we would get metric would be 1, like the g plus minus. So we would get this minus the Lagrangian. So here, like the term in plus derivative would cancel, and we get only this part with the minus because it was minus Lagrangian. But again, with the part with the plus derivative that cancel. So that's what we get in terms of the derived field. But now if we write separately the good and bad components, there is one part with the gamma minus which project out the good component, and we get only the bad components. And then there is a part with either this or minus the mass, which has no gamma plus and no gamma minus. So basically now what we have is that it's only mixed terms, like bad good or good bad here. So we have these three contributions here to the T plus minus. So now you see you have like, so this is associated with eventually to dynamical transformation, and now you see you have the bad component which is there. But then okay, you can use the fact that the bad components can be written in such a way by solving the constraint equation. And okay, if we plug this into each of the terms here, eventually we can write that. I mean, we can basically use the solution of the constraint to eliminate completely the auxiliary bad components and write everything in terms of the good one, and we get something like this. But now this becomes non-local, you see, because there is this inverse minus derivative. So this basically means that there is a convolution along the minus direction here. So effectively now, if you write down your Hamiltonian like the P minus, instead of being integration of a local operator, that would be something kind of bilocal, at least in the minus direction here. Okay, so, but okay, apart from that, there is no problem. And now, again, we would like to see if there is any problem with the construction of Fock space. So here, like the psi good still have two components. And actually, in order to, like the only thing which, only place where we use these two, I mean, like the main place where these two components start to talk to each other, at least, okay, in here, there is nothing. I mean, like, since there is only gamma plus here in the middle here there is nothing special. It's only here there is this gamma I, gamma j, which okay, is doing something kind of non-trivial between the psi g and psi bar g. And okay, so if you study that, okay, like remember that this was appearing when you in this generator of rotation within the transverse plane. So basically this guy here, yeah, and indeed it was coming from that, which was like the object which is used to describe yeah, how Lorentz transformation. So in that case, this particular rotation within the transverse plane affects the components of the spinor. So basically, yeah, and
Yeah. Could the non-locality cause something bad with causality?
I mean, at least it might be, yes. Okay, I don't know. It's in principle it's not clear, but then since the thing that all this construction is in principle studying the same theory as when you do evolution along a time-like direction, like in instant form. So it's a different parameterization of the same theory. So it should be completely equivalent. So by the argument that it should be completely equivalent, if the other one has no problem with causality, this one should not have problem with causality. But then to check it explicitly, okay, I'm not sure how I would do that. Yes. So okay, so it's more argument that okay, there should be no problem, but yeah, I'm not sure exactly how to. Okay, we have to think about one way to check or yeah. Okay.
So it has not been done.
Okay, I don't know. Honestly, I don't know. Probably some people have discussed that somewhere, but I don't know all the literature.
There are recent papers by this guy in Connecticut by Philippe.
Philippe Monheim.
I think Monheim that they showed the complete equivalence of Light-Cone quantization.
Yeah, okay. At least in terms of free field, yeah, they show a complete equivalence. Yes. So yeah, again, it's equivalent. Okay, there is no problem in one, there should be no problem in the other. But yes, again, it's in here it's not necessarily obvious. Yes. So yeah, so basically here this guy, it happens that that is, so this would be a 2 by yeah, okay, a 4 by 4 matrix in principle, but then if we project it on the good components, that would be we would get a 2 by 2 block out of this 4 by 4 matrix, and then this 2 by 2 block can be diagonalized actually, and there are two eigenvalues which are +1/2 and -1/2, and this actually corresponds to really kind of helicity, like helicity that you have in your for your Dirac. I mean, yeah, for the quanta of this Dirac field here, but more precisely, that would be helicity. That would be what is called light front helicity, which is projected not on the momentum of the particle you look at, like what would be the case of standard helicity, but instead is projected on the collision axis. So basically on the third direction, the one which is used to build X plus and X minus. So okay, and so basically we can write two eigenvectors of this. So which has this so we have this helicity here, which is this h, which can be like this light front helicity h, which can be plus or minus 1/2. So okay, that's allowed to classify things, and so basically now we can use this UG with plus or minus 1/2 as a basis for your for the two-dimensional space that your good component psi g can cover basically. Okay, I also to introduce that particular normalization, which should be useful later, and I can also introduce okay, just again for later convenience, this V instead of like VG instead of UG, which would just be the one with the flipped H. And now I would have also the following completeness relation here for this vectors here. So now okay, so there were like, so these are two-dimensional vectors, and when I do that and sum over the unicity here, I would recover the identity in these two by2 blocks, so that's this psi g and up to this normalization there. Okay, fine. This is technical, but then that would just, that now with this, I can define this B dagger, D dagger operator here by just this Fourier transforming along the minus and perp direction and applying this this thing here to further project the psi good field here. And okay, obviously this so yeah, or we can invert that as well, and then the psi good component here can be written in such decomposition. So here it would start to look really familiar here. Okay, and then okay, by using the commutation relation I was writing before for the psi good and its conjugate, we can also check that we have this two non-trivial commutation relation, like anti-commutation relation, sorry, and the other one will be trivial. So really this B dagger and D dagger, okay, really correspond to annihilation and creation operator for the basically fermion and anti-fermions as usual. But now, okay, now the thing is that since now we have only two components here, and so okay, so that really so that's why we have this this guy here with okay, again we have both psi and the UG and VG, which are two objects with like vectors with two components instead of four. We have removed the bad component here. So now, since kinematic Poincare generator, we saw that they could be written only in terms of the psi g components. We can also rewrite them entirely in terms of the B and D dagger and D and D dagger. And okay, like the same thing can be done as in the scalar case. So I like to study how to normal order these things and see that it will be normal ordered up to a constant which will eventually vanish if you regularize the UV properly. And for example, for the P plus or P perp momenta at the quantum level, that can be written in such a way here. So with B and D in the normal order, so you will get contribution from the fermion and anti-fermions here. And again, we can define the vacuum for the same reason as yesterday for the scalar, but just by being the thing which is annihilated by both the B and the D annihilation operator. And again, all this construction was done at some given X plus here. And again, we have the same story that we can construct the Fock space at each given X plus, because we have the vacuum here, which is defined in such a way, and then we can act with D dagger and D dagger instead to create like other higher Fock states and so on. So everything works very similarly. Of course, you have to be careful with the anti-commutation and signs and this kind of thing, but apart from that, it's very similar to the scalar case, at least for that part. Yeah, and the thing that all this construction here, I mean, like most of what I was talking, except for the okay, except for this discussion of the T plus minus and of the particular form of the constraint equation and of the expression of psi b in terms of psi g, all the rest is only about kinematic components and kinematic operators and psi good components, and that's so that would so that was done for the free field, but that would still be valid. So that's all independent of the Lagrangian here, like this term was disappearing. And so all this would be still the same in an interacting theory. So basically only the constraint can be a bit different, and this guy here. But the rest, what I was telling is will still valid in an interacting theory with some Dirac field on the light front, obviously. And now just so yeah, so that was it. And then just for later convenience, okay, we can also study now if we really specifically talk about a free field, we can also perform the, I mean, yeah, we can also, okay, instead of looking at just one given x plus here, we can also Fourier transform with respect to that, because we know what the evolution in terms of along x is just given by the free free Hamiltonian, and so we know that the eigenvalue in terms of minus would be just the free on-shell value here, and so we can write a free field here in such a way, and now these guys would be the more usual U and V pinors, which if you project them with P goods, will get the UG and VG that I was talking before. So this now is really a 4-component field, but this is but this can be written only for a field which is free. Whereas psi good, we could write a decomposition in terms of UG and VG for a field in the light front, but in general it could be free or interacting. And now, okay, like the UG and the U and V standard free spinor, okay, they obey the free jet equation in momentum space like this. So this is really the standard relations, and yeah, and just okay, here we say that if you project them with a psi good, you get this UG and VG, but then because of that, they would have also contribution with they would have also bad components, and we can basically solve this in order to get the bad component of this U and V in terms of the good and bad, and so that's just the relation we get. So we get this for the spinors, and the conjugate of this equation will give you this. So and okay, and then we have a usual completeness relation now. In terms of this 4-dimensional vectors U and like spinor vectors U and V, instead of the 2-dimensional I was showing you for at the level of UG and VG. So that will be useful. So this was specifically, so this small section was specifically for free field, but as we will see later, it will be quite useful when constructing actually QCD, for example, or QED. So I think it's probably time to stop, right?
Yeah.
That's okay. So okay, we'll continue this afternoon with the free photon, and then finally QCD. Yes.
Thank you very much. Any questions? There's one on Zoom. Okay, I will take it, yes.
Yeah, okay, then to follow the order will be
Okay, yes, but I've forgotten this of the video. I will take the picture. Any other question? Will I take the picture? It's not really right.
When you make the 3-particle derivation, there's a term that so the 2 goes to, for example, 2 goes to 4, and then the intermediate particle would be a loop that are attached on the line from 1 to 3. is that one dropped?
Right, so two.
So it's like 2 equal to B equal to 4, and then
So that will be spectator, so that will not participate in the vertex, but I will be like what I did. So there will be vertex which we want to A and 3, we split into A and 3 and C, sorry, and then 2 will be just D. Right?
yeah, 2 to B, and then the AB dagger to 4. So then 2 and 4.
Maybe you can draw the diagram.
Okay.
Yeah, okay, yeah. I see, yeah, okay, so that I was not indeed. Here I was, okay, here I have the disconnected part, which was no interaction here, but even in the interaction piece, we can still have a disconnected contribution here, and indeed that's something to get into account here. Yeah, so here I was focusing on the connected part of the scattering.
Okay.
That would have this, which, okay. Okay, if it was only, if you can see this was only on the, not on the scattering amplitude, but on the waveform function, I know that this would be the diagram which should contribute to the waveform normalization factors, Z. So here in the amplitude, okay, I'm not exactly sure what that would mean, but that would be still probably again related to this normalization factors. Yes. But okay, it's not. I have not really done that kind of calculation, so okay, like the precise relation, I'm not exactly sure, but it could be that, yes.
Would that be something similar to normal continuous area that you have some denominator to reduce or simplify this diagram? Just at the end of the day, you have some self energy or something like that. And just absorbing the renormalization, some reduced math.
Yeah, it's like self-energy correction.
Yeah. So it's
Yeah.
similar to the normal.
Actually, yeah. So that might also contribute to mass renormalization. Yes. So yeah. So mass renormalization for sure, yes, and maybe as well wave function renormalization factor. But I'm not sure if we. Yeah. Okay. We have to look at this example more precisely to see what's the same. Yes. So.
Some other question through Zoom? Okay, if not, let's thank Guillaume. We'll come back in the afternoon. Okay. See you.